Hello, everyone. Thank you for joining and welcome to this DataHour session. So, as you guys probably know, we'll look into semantic segmentation. We'll learn the various techniques, the challenges, and the associated methods. So, I want this session to be a bit interactive. So, like, feel free to ask any questions in between or at the end, since we have a Q&A. And yeah, without further ado, let's get started. I'll just share my screen. A brief intro about me. I am currently working at Airtel Africa Digital Labs and have almost 4 years of work ex. And mainly, like the key area of expertise is computer vision, uh, and in that, object detection, semantic segmentation, and many other related tasks. I've also worked on NLP, audio data, and yeah, related disciplines. Like, let's start with the agenda for today. Basically, we'll start with the introduction, wherein I'll cover the basics of semantic segmentation and its applications. Then I'll move on to the techniques and the neural network architectures which I use. After that, we'll actually be training and evaluating a semantic segmentation model from scratch. We'll look at the data collection, the data processing, training the model, and how do we actually end up evaluating the metrics and decide which model to use, right? And finally, we'll look at some of the state-of-the-art methods which are publicly available. And yeah, and finally, we'll look at some of the common challenges in semantic segmentation and how do we, address them. So yeah, let's get started. Now, before starting with semantic segmentation, let's take a moment to review CNN, which is kind of the basic or the fundamental building block of computer vision. So CNNs are like really well suited for image analysis or related tasks such as object detection, image classification, and semantic segmentation. So what happens is in a CNN, an input image is fed through a series of convolution layers, uh, which applies filters to extract important features from the image. And then these features are passed through fully connected layers, which produces a final output, which we call a classification label. And now the core component of a convolution layer in a CNN is the convolution operation. Let's like look in detail on how it works. Let's consider an input image. So this is 6 by 6. So technically it should be 6 by 6 by 1. It's a single channel image, and we have a 3 by 3 filter. Now by convolving this, what we are essentially doing is we are superimposing this 3 by 3 filter on the first 3 by 3 channels of this 6 by 6 image. So you can imagine putting this on these three. And now what we'll do is we'll multiply the corresponding numbers. So 3 gets multiplied by 1, 0 gets multiplied by 0, and so on. So after taking the products, we will add all these elements to get our final result, which would come here. So this all converts to -5 using this filter. After this, we will move this filter one step to the right and again perform this operation on this 3 by 3 region. And we will do this until we get to the final result. So what essentially we are doing with this operation is, if you see that we are downsampling the 6 by 6 image into a 4 by 4 image while preserving the important information. So this is the core of how a convolution operation works. And in general, like CNN has really revolutionized the field of computer vision and had many breakthroughs uh, in different fields, and semantic segmentation is one of it. And yeah, the convolution operation is the basic. Uh, Now the question lies, that why are CNN so powerful? We already had ANNs, right? The basic neural network is an artificial neural network, ANN. But why do we use CNNs then? Now, the reason is ANNs process all inputs in the same way, regardless of their input space. So basically, if you want to process this image using an ANN, first of all, it's not possible this way. We will need to flatten this image into a single array. So right now it's a 2D array. We would need to flatten it to a 1D array. Then we can use this type of network architecture, which I'm highlighting, to process the image. But again, so the thing is, while using CNN, we can take advantage of the spatial structure of input data. This happens due to this filter that we are using. So this filter, instead of working on a single pixel at a time, works on 3 by 3 region at a time. And basically, this introduces a concept called receptive field. So instead of working on a single pixel, it has a receptive field of 3 by 3, uh, which like helps in learning the spatial features. So due to this property, CNNs are really good at capturing local patterns in input data, which can be like really useful in many computer vision tasks. So uh, let's see. If we consider a network, CNN network, the first few layers of the network would produce some features like this. These are pretty low level features like horizontal edges or vertical edges, or maybe some dark spots. Now, as we go deeper into the network, like some of the layers tend to output some mid-level features like partial eyes, as you can see here, or partial nose, and so on. And towards the end, we get really high-level features like actual faces. So in conclusion, these are the CNNs are really good feature detectors. So we can put it this way. And like we can see an example of a basic CNN network. So this is called LANet 5. It was one of the very first CNN networks ever developed. So this was actually developed for handwritten digit recognition. And like it was one of the very first networks that actually achieved state-of-the-art performance on a computer vision task. So this architecture consists of 7 layers, including 2 convolution layers, 2 subsampling layers, which are also called as pooling layers, and 3 fully connected layers. Uh, it says LANet 5. Uh, you might say that why does it have 7 layers? So the thing is, the convolution, sometimes what happens is in literature, the convolution and subsampling layer, which is also called the pooling layer, these are combined like called as one layer. So this is a single layer, this is the second layer, the third layer, and finally the fully connected layer and output layer. So that makes up 5. Now, as I said, it was originally uh, like created for handwritten digit recognition. So the input to this was a 32 by 32 grayscale image, and the final output was the probability distribution over 10 possible digits. So let's say if we have an image 8, so the output would have probabilities with the digit 8 having the maximum probability, provided the network was trained uh, like really well. All right, let's move on. Now, looking at different problems in computer vision. So basically, there are many different kinds of problems. We start with classification, which is the starting. Basically, we are given an input image and we want to detect uh, what is inside the image. So in this particular example, let's say it's a cat or not. The next problem is classification plus localization. So here we not only want to classify it as a cat or not, but we also want to locate where exactly is cat inside this image. So as you can see here. Now the next one is object detection. So in case of object detection, it is pretty similar to classification plus localization. The only difference being that it can have multiple objects detect that can be detected in the same image. So here you can see there's a dog which is detected, there's a cat, and there's a duck as well, which is hardly visible, but yeah, yeah. All right. So the next thing is semantic segmentation, which is also the topic for today. So in case of semantic segmentation, as you can see from the image, we are detecting different objects, and instead of like putting a rectangular box over the image, we are delineating the exact boundaries of the object and doing it very precisely. So this is the key difference between object detection and semantic segmentation, that we want a pixel level accuracy of each object, right? After that, there's another problem called as instance segmentation, which is kind of like an advancement to a step ahead of semantic segmentation, wherein uh, so in semantic segmentation, if we have two objects of the same category, so let's say if there are two cats, we will both like we'll label both the cats in the same category. We'll call this one as cat and other one as cat. But in instance segmentation, we'll label both the cats as different. So this will be cat one, this will be cat two, dog one, and so on. Right. So let's move on. All right. Now, since we saw a basic idea of what semantic segmentation does, now let's move on to an overview and how it is done. So it's basically a technique of dividing an image into regions or segments, and we are assigning each of those regions or segment a corresponding label, right? In other words, uh, it is a type of image segmentation that involves assigning a semantic label to each pixel in an image. So it can be viewed as image classification, but instead of classifying the whole image, we are classifying each pixel individually, right? So this is a like crucial task in many computer vision applications. As you can see this image, it can be used in autonomous driving, medical imaging, and surveillance. This particular example is of autonomous driving. So, of course, in case of autonomous driving, you'll need a lot more things, but this is a like the basic block of how it works. So, essentially, here we are detecting like roads, we are detecting trees, and not only detecting but locating the exact pixels. So this is very useful. As you can see, when a driver is driving, we have the a measure of the distance between our car and the other person's car, and this is how we can build logic over it to create our self-driving cars. Yeah. Similarly, it can be used in many other fields like medical imaging, car damage detection, etc. So, semantic segmentation can be of two types. One is binary segmentation, and other one is multi-class segmentation. So, in case of binary segmentation, we are classifying. We only have a single class in our image which we want to detect and uh, locate. So, in this particular case, the one I'm highlighting, we are only detecting and locating person in an image. So there are three person, and this one is the corresponding mask associated with this image. This is the binary segmentation. The other one, which was also shown in the previous example, this is a multi-class segmentation. So here we'll segment more than one classes. Uh, so here you can see there are a lot of classes: roads, cars, trees, buildings, poles, etc. Now let's move on to the techniques on how do we perform this method. And before actually moving on to the actual techniques of semantic segmentation, let's look at some of the building blocks. So as we saw earlier, there's an operation called as convolution operation, which is used in CNN. The core function of a convolution operation is to downsample an image while preserving the important information. So apart from convolution, there is another method called pooling, uh, which also does kind of downsampling, but in a different method. So this example shows max pooling. If you look at it here, uh, we are we are having a 4 by 4 input image, and using this max pooling filter of stride and filter 2 by 2 and stride 2, we are reducing this into a 2 by 2 image. So how does it work? Basically, if we like, since we are taking a filter of 2, we'll look at 2 by 2 region at once. So if we look at this, we see that the maximum value of the pixel is 9. So we'll select 9 from here. And since the stride is 2, we'll move 2 steps to the right. We'll select maximum from here, which is 7, and so on. So basically, what we are trying to do is we are trying to downsample the image. And what's the like rationale behind using this method, max pooling? So like the brighter the pixel, so the brighter the pixel, the more important information it has. So this was the like basic rationale. So since 9 has the highest value, we'll select 9, and it has the most information. And like the very less information would be lost if we use this kind of method compared to if we choose any other pixel. Now, apart from downsampling, there's another building block of segmentation called as upsampling. Now, since we want to use like recreate a mask over an image, we want to upsample as well. So there are various methods used for upsampling. The most popular one is deconvolution, which we also call as transposed convolution. So let's take an input, let's take an example here. So let's say we have an input of 2 by 2 and a kernel of 2 by 2. The kernel of 2 by 2 is most popular in case of deconvolution. So what essentially we are doing is we will take this first pixel 0 in our input, and we will multiply this pixel with all the 4 pixels in the kernel and put it here, right? Uh, and then we'll move on to the next pixel, which is 1. We'll do the exact same thing. So we will multiply uh, 1 with 0, then 1 with 1, 1 with 2, and 1 with 3. This would get here. Now moving on to the next pixel 2, we will do the exact same thing. We'll multiply all these 4 numbers with this and get this one. Finally, we will take this 3 and multiply it with this one and get this one. Now finally, we'll add all these 4 matrices to get our final matrix. So essentially what we have done is we have taken a 2 by 2 input and converted it to a 3 by 3 image. So kind of upsampled. This is a really popular technique. There are other techniques as well, like nearest neighbors, bilinear interpolation, bed of nails, and max unpooling. FCN is our first technique that we're going to study. So this is a technique used for semantic segmentation. Essentially, these were very like one of the very first neural network architectures that were designed for this particular type of task. It consists of a series of convolution layers that downsamples the input image to 132 of its original size. So like if we have an input image of uh, like x comma y comma 3, where 3 represents number of channel, we will apply a series of convolution and pooling layers so as to reduce the spatial resolution and extract only important features, right? So due to this uh, convolution and pooling operations, we are reducing the input image and keeping only the important features, and this happens until this step. uh, After that, what we do is now we have all the important information that is present in this image. Now, our task is to get this information to the same level as the input and like get the exact location of those individuals. So let's say in this particular case, we want to detect the grass, we want to detect the trees, the cows, and the sky. So at this point, which I'm pointing out, the information is in condensed form. After this, we are expanding this information, and this expanding or the expansion path, which is also called as the upsampling part, is going to expand this image and uh, finally we'll reach the same size as our input image. So this would produce what is called a segmentation mask. So this segmentation mask is basically the output of a semantic segmentation model. And what is this is like referring is a pixel level classification. So all these tree like regions are marked in pink color. So all these represents tree. Similarly, this blue one is representing sky and the cows and the grass. As we already discussed the convolution uh, operation earlier, so that's how is it like how it happens. Like FCNs are really efficient and easy to implement. Uh, as you can see, another point that I missed is actually this type of network is also called as an encoder decoder network, as we are encoding the important information from an image and then we are decoding it back to its original size. So yeah, that's another name for this type of network. Now, as I was mentioning, that FCN are easy to implement, but can sometimes produce coarse or rough segmentations. And this happens due to like information loss while upsampling. Since we are using an approximation method for upsampling, it doesn't always, produce the best results. So this is an example of a coarse segmentation mask. As you can see, it is pretty rough. There are a lot of patches and non-continuous, pixels here and there. So yeah, that's the limitation of FCM. Like, let's move on to next technique, which is called UNIT. So this is a modified version of FCN architecture that used skip connection to solve the problem that we discussed in the previous slide. So it uses skip connections between the encoder and decoder layers. So like these skip connections the allow to preserve the high resolution features. So what happens is, like if you see this network, like is very similar to the alphabet U. That's why it was called UNIT. What essentially is happening here is we have an input image. We are applying convolution operations. So this 572 by 572 is getting downsampled. After that, we are applying a max pooling operation, which with a stride 2 and filter size 2, which is exactly reducing the image size into half. So this 568 gets reduced into 284. So and so on. So this is a continuous step which is happening. We are applying a set of two sets of convolution operations and then a max pooling, again two sets of convolutions and a max pooling, and so on. This happens till the steps when the image size is reduced to 32. After that, there's a concatenation stage, and then we start the upsampling. As you can see, these gray lines, these represent skip connections. Now, what it helps is the neural network to preserve like really high resolution features. So the neural network now has two pathways to reach this output. In one, like the network can traverse through this path and can also traverse to this path directly without losing any information. So this proved to be very beneficial and provided like really accurate results. Originally, this type of network was designed for biomedical image segmentation, and hence it is particularly effective for segmentation tasks with really small objects. Let's move on to the next one. This is called SegNet. So it's again a modified version of FCN architecture, but instead of using the skip connection, it used something called as pooling indices. So it stored the indexes of max pooling operation and used those to transfer the information between encoders and decoders of same resolution. Again, this was done to preserve the spatial information. And one downcoming of unit which it overcame was that unit was a bit slower if we try to run it in real time. Segnet, however, proved to be really computationally efficient and is like really successful uh, when using in real time tasks. So there are several other segmentation network architectures apart from the ones that we discussed before, like Segnet, Unit, and FCN. There is one called DeepLab. So it's a series of convolutional neural network architectures which was developed by Google. It had V1, V2, V3, and V3 plus. So there were four networks with DeepLab. It used something called as address convolution to capture multi-scale contextual information. Like I have linked these papers, which you guys can probably check out to read in more detail. Then there was PSPNet. It used something called as pyramid pooling module, again to extract information at multiple scales. Then there was RefineNet, uh, ENet. Now, ENet is again a really popular network architecture for real-time segmentation, as is ICNet. Now, these are just a few examples. There are many more segmentation architectures that have been proposed in recent years. Now, each network has its own strength and weakness, and the choice will probably depend on the requirements, specific requirement of the application. So I would suggest you to explore on your own and yeah, try out many architectures and see which one works best for your use case. All right, now let's start with training and evaluating a segmentation model. Now, the first step in any deep learning or data science project is data collection and data tagging. So for that, first we need to define the problem and identify what type of data is required. So let's say we want to build a self-driving car, like a segmentation model which like identifies uh, cars, roads, and buildings, and so on, and probably traffic signals, etc., so that like the car can take necessary actions. So if you want to make a model like this, so like after this we'll cover some Q&A. I think there are some questions. We can cover it after this section probably. Right. Yeah. So as I was explaining about data collection and labeling, so let's say this is an example image which we want to label. How we going to do that is using some, there are many tools, open source tools available for data labeling for this segmentation. One of which is really popular is via image annotator, which I can just show you how it is. So this is an online tool, which is really easy to use. So how the data is labeled is basically I have uploaded an image here. I have created some labels. Now what I need to do is I need to draw the exact boundary. So I'll just show you a demonstration. So as you can see that I'm kind of marking this as a polygon instead of like really accurate pixel level, but this works well for most cases. Yeah, now I can assign a label as car. So yeah, and now I'll start labeling another field. Let's say I want to label person. Like as you can see, this is a really time consuming task, and it requires really high precision if you want to get a really good accuracy. I'm going to label this as and so on. So this is how you can label your data. After this, this allows us to export our annotations in a JSON format, which we can then use to create a somewhat approximate mask around this. Right. So moving on. So for this particular demonstration, we'll take an open source dataset called Carvana Image Masking Challenge. So this is a 5-year-old challenge. Carvana is a car company which uses rotating photo studio that automatically captures 16 standard image of each vehicle. They wanted to develop an algorithm which removes the background really precisely, so that they can use this image to uh, use various kind of backgrounds and present it in a showcase. So I'll show you how the data looks like. So these are sample images, and also these are the masks associated with these images. So as you can see that here only there's a single label basically. There's obviously background, but we only want to detect and locate a car. So this problem is called as binary segmentation, and it's not multi-class since there's only one class. Now in the data set, there are a variety of car models. So this one is a sedan type car. This again a sedan. This is a hatchback one. So as they mentioned, there are a variety of makes models available in this data set. Let's start with training. I'll just open up the notebook. All right. Meanwhile, it opens up. Till the time it opens up, let's discuss the architecture. So this is a simple unit model that I've built uh, using Keras. So these are standard imports that we are using. And yeah, since as we saw in the image, this contains a series of convolution layers and a max pooling layer, which is what we can see here. There are convolution layers, then there's a max pooling layer, and this goes on till we reach the size, uh, till we reach the fifth level. And after that, there's an upsampling part or expansive part where we are upsampling till we reach the final uh, segmentation mask, which has the same size as input. Now, we are using sigmoid layer as our activation of the final layer since it's a binary image segmentation problem. And the final output is, as you can see, it's one. So it will be either it's going to be a probability of or one at each pixel. If we were doing a multi-class segmentation problem, then it's going to be softmax instead of sigmoid. And this one would be the number of channels. So let's say there were 5 different classes we wanted to predict. This would be 5 instead of one. We'll look at that example later. But yeah, this is the architecture. So this is a very simple image generator that we are using. We are reading training images and masks from the directory. Uh, I think the data originally contains around 5,000 samples. So for faster processing, I'm using only 1,000 samples. So we are basically opening up the image and converting it to RGB and then resizing it to 256 by 256. Uh, so there's no particular reason for this 256 size. Like you can experiment with more. You can take up, let's say 500, 512, 300 cross 300 and so on. So the input image can have like different size, and different sizes would produce different levels of accuracy. So the bigger the size, the higher the accuracy there would be, but the execution would be slower. Right. So yeah, we are loading images and masks. After that, here, like you can plot some of the images. So I'll see if I can take a smaller set to load it right now. So right now I'm only taking 100 images. It's running really slow. So what happens is in Collab, the disk operations are really slow. So it's advisable to do such operations, on probably a server or a local machine. So yeah, let's look at some questions while it's loading. I think slides would be shared at the end. Yes. And I'll also share the link to Jupyter Notebook. I think we are using transpose convolution. Yeah, I think I mentioned transposed convolution. Okay, there might have been some typo in writing. Yeah, I think you're right. Transposed convolution is different. I mean, deconvolution is different. So I actually meant transposed convolution. Right. So in this step, we are basically, creating we are loading all the images and masks in a list, which will then use to train our model. So I'm only selecting 100 images at this point. The more you select, the better the model would train. Uh, but yeah, due to the time, like the time it takes, I'm selecting fewer images. So like using this one, we can randomly sample training data and labels. So as you can see, this is an image, a sample image from our data set, and this is the corresponding mask. Again, yeah, this is another image, and this is the mask. So yeah, uh, so for data processing, we are normalizing our image, which is this pretty much the standard for any computer vision or CNN problem. Uh, we normalize the image from like having the pixels 0 to 255 to 0 to 1. And for mask, we only have 2 pixels at the moment. We have 0 and we have 255. So we are reducing since we have our image in 0 to 1, we are also converting this 255 to 1. So instead of 0 and 255, we'll be having 0 and 1. So this is what this is doing. After this, we are splitting our data set into train and test. This is pretty much standard. And yeah, we are building our model using this function that we had above. We are compiling using Adam optimizer and binary cross entropy loss. So this is the same for image classification problems as well. We use binary cross entropy for single class problems, and for multi-class we use categorical cross entropy. And we use accuracy as our metric. We can see the summary of our models, and yeah. So I ran this notebook some time ago, like probably yesterday. So this notebook uh, uses yeah. So I used a batch size of 16 and 20 epochs for this network, and I think I trained it on a like 1,000 image data set. So out of this data set, I selected 1,000 images, and I trained it on that. So yeah, as you can see, we achieved 98% accuracy for training and 98% validation accuracy as well. So I'm not going to run it at this point since it takes some time, but I'll share the notebook for you guys to play around. Uh, yeah. So after this training, I evaluated the performance on test set. Since we splitted our data into three parts, we had the train, test, and val. So the final test set has a accuracy like of 98% that we get. All right. But this is not the metric that is commonly used for evaluating segmentation models. There's something called as IOU that we'll just discuss it. So commonly used evaluation metrics for semantic segmentation models. So what in IOU, what we do is we take the two masks. We have our original mask, which is the ground truth, and we take the predicted mask. So for a particular class, we calculate the area of overlap between the ground truth and the prediction, and we divide that over the overall, or I mean the total area of union. And by doing this, we get an estimate of the how much there is an overlap. So for a perfect mask, this value would be 1, and for a like really bad mask where uh, there's no overlap, this would be 0. So this is a really popular method used for evaluating the performance of segmentation models. Apart from that, there are some more methods like dice coefficient, which is almost similar to this method. Like uh, it has a similar expression as to F1 score, which is the harmonic mean of precision and recall. Like this method is more sensitive to smaller objects, the dice coefficient. So it all depends on use case. Then there is pixel accuracy, which is probably the simplest method. What we are doing here is so as we do in classification at the image level, here we'll be doing it at a pixel level. We will look at the ground truth and the uh, like uh, actual prediction, and we'll compare each pixel individually. After that, we will calculate, okay, how many pixels are correctly labeled, and using that, we will do the accurate number of pixels divided by total pixels to get a pixel level accuracy. Finally, there is something called as MIOU, or mean intersection over union. So this is particularly used for multi-class segmentation models. So this is IOU, but for but averaged over different classes in our data set. So let's say we have 5 different classes that we want to detect. The example that we saw earlier was for a binary segmentation. But let's say we have 5 different classes. So we will calculate IOU for each individual class and calculate the average to get the mean intersection over union. And this is probably the most common method that is used for uh, evaluating the performance. So let's look at this site that I want to show it quickly. Uh, this So this is a really popular site, Papers with Code, which lists the various data sets and the benchmark performances. So I've opened semantic segmentation. So there are a lot of open source data sets available for this problem. Cityscapes is a really popular one. So let's look at this. So here we can see different models performances, which is which are using it uh, I mean, which is using MIU as a metrics of evaluation. So mean IOU, as we can see that we are filtering we are sorting by mean IOU. So 85.2% is this model weighted after L. This has highest mean IOU for this particular data set. And yeah, you can see many different models which gets released uh, like really often nowadays. And yeah, there are many models. So deep lab, as we were seeing earlier, this has a good accuracy but not so good on this particular data set. So this is this kind of problem. The semantic segmentation is dependent a lot on the type of data set that we're using. uh, let's move on. Yeah, let's quickly go through the challenges in semantic segmentation before we move on to the Q&A. So one of the primary challenges, as we saw earlier when I was trying to show you how to label a data, that getting an annotated data is really time consuming. It requires humans to accurately label each pixel. This is really time consuming. So this limits the amount of data which is available. So this is one issue. The other one being class imbalance. So let's consider this image. Now, as you can see, the pixels of the road in this are like much more compared to pixels of this pole. So this pole has probably like maybe less than 10% of the pixels of the road. So this creates this huge class imbalance issue. So model has no particular incentive to detect pole. Even if it doesn't detect pole and detects, let's say, the classes below this one, it will still get higher enough accuracy. So that's one common issue with it. There are techniques to solve it, like data augmentation, class weighing, which I won't cover here, like at this point, but yeah, you can probably go through it. The other issues can be occlusion. So let's say we want to detect a car, but there's a person standing in front of the car. So this kind of image wasn't probably seen by the model in right, like at the time of training data. So in this case, the model probably won't work that well. And yeah, another example is ambiguity. So sometimes it's really difficult to identify the exact boundary of an object. So let's say we want to create a model, a segmentation model to locate dents. So here, like it's not exactly clear how far or like how far does the dent go if we want to label that. So there's a bit of ambiguity in there. Yep, there are some other uh, problems as well, like computational complexity. So these models like are really computationally intensive and requires large amount of memory and processing power. And they are also less likely to generalize on a particular, like they can be generalized on a specific data set, but it tends to fail, on other types of uh, real world cases. I can show an example quickly, which I tried it using this model. So I tested this model's performance on some external images. So as you can see, I tried it another type of image which had a different background. So the original dataset has this very specific Caravana background. So the model performs very well. This is the prediction. So this is the original image. This is our testing label, the ground truth, and this is the prediction. The model performs very well in this case. But if we look at some of the predictions of the images like this, where there's a different kind of background, the model falls apart. So yeah, it's very difficult to get a generalized model. Instead of unit model that you have customized, can we use any pre-trained model for image segmentation? So yeah, that's one thing that I like didn't mention, that it's always better to use pre-trained models than training our models from scratch. So this also solves for problems like uh, the problems like class imbalance, because originally the model was trained on very balanced data sets and very large data sets. So it's always advisable to train on pre-trained models. Uh, for UNet, if you want to do that, there are like pre-trained models available for different kinds of problems. So yeah, like you can find many repositories which have pre-trained models for various cases. So I think there's one available for biomedical image segmentation. You can download that pre-trained model and start your training from there. I'll probably link that somewhere in the PPT for you guys to explore. Telecom industry, okay. So the question is that what are the representative use cases of semantic segmentation in telecom? Like I'm not sure on telecom. Okay, one problem that it could be used in is uh, probably ID card segmentation. So like what happens is that we have uh, there are a variety of problems available for in telecom industry. One of which is detection, like OCR, like using OCR on the ID card to extract relevant information. But what happens is the ID card is, like in most of the cases, ID card is like not in a proper form, or it has many background elements as well. So you can use probably semantic segmentation to get the exact pixels of ID card, and after that perform other methods. how do we use transfer learning models used for semantic segmentation? Yeah, I'll link some of the repositories that have pre-trained models, and you can use that. Thank you.